I really wonder in reading a cartoon like this if the little blonde-haired boy is really that smart or if the teenage boy is really that dumb. If you need more time to read the comic, just pause the video. Our final section in Chapter 7, 7.5 Applications from Science and Statistics. Now, we talked about how volume is a major application of integrals. But only slightly less than that are applications in science and statistics. Those of you who have had the wonderful pleasure of having Mr. Rowland's statistics class, we are going to do some normal probabilities, perhaps easier maybe than what you had to do when you were in his class. Calculus makes life easier. We're also going to look at the concept of work and fluid force, fluid pressure, some interesting historical facts for today. Not a whole lot of slides. We'll see how long it takes us. Example 1. Finding the work done by a force. Find the work done by a force f of x equals cosine pi x newtons along the x-axis from 0 meters to 1/2 meter. Now, normally when we do a work problem, we just do force times distance. But that formula always assumes a constant force. When you have a varying force, a little bit more force here, a little less there, then we're going to do force just like we did volume, just like we did area. We look at instantaneous measurements. In this case, we'll do instantaneous forces. And we'll add up all of those forces along the way. So what we'll do is we'll take the integral, because again, that's how we add things, from 0 to 1/2 of the force function cosine pi x dx. The integral or antiderivative of cosine pi x is 1 over pi sine pi x from 0 to 1/2. Plug in your 0 and your 1/2, although I'll always remind you that you can plug this into your calculator. We have this right here. Sine of 0 is nothing. Sine of pi over 2 is 1. And that gives us a final answer of 1 over pi Newton meters, or instead of Newton meters, we can say joules, if you know what a joule is. Next problem. Leaky bucket weighs 22 newtons empty, lifted from the ground at a constant rate, and so on. And you can continue reading the problem, but essentially what we're going to do is we're going to work one major problem, this whole problem of lifting in different parts. First of all, we're going to find the work done just lifting the bucket by itself, water excluded. Then we're going to figure out the work of lifting just the water, no bucket, no rope. And then we'll find the work done lifting the rope, and then we'll put them all together. Now, let's talk about the bucket. The bucket weighs 22 newtons, flat out constant no matter what. It's not going to lose part of its weight as the bucket's lifted. Just the bucket, 22 newtons. And we are lifting at 20 meters. So 22 times 20 is 440 newton meters, or joules. Now, let's talk about the force done lifting the water. It does say that the water is 70 newtons. But mind you, that 70 newtons is the starting amount. It starts with 70 newtons, about 7.1 liters of water. And it is leaking out at a constant rate, and it finishes just before you hit the top. So here is what I came up with. Remember, you're going 20 meters. At 0 meters lifted, that's a 0 right there as an x, you would have 70 times 1, so you'd have 70 newtons. At 20 meters lifted, alright, I would put a 20 in for x there. 1 minus 1 would be 0. You would have 0 water left. So this is my formula representing the weight of the water, or the force of the water, I should say. Alright, distribute the 70. 70 minus 3.5 x newtons. Now the work done by the water, we'll take the integral from 0 to 20 of that force equation and work that out on your calculator. You get 700 newton meters, or joules. Alright, now what about the rope? Well, the rope, if we go back here and we look, it tells us that the rope is 0.4 newtons per meter. It weighs 0.4 newtons per meter. So 0.4 newtons. Now again, how do I represent the meters? Well, again, at some point, if I think about some amount raised up x, I could represent that distance raised by 20 minus x. Got 20 to go, and I've already taken off, some amount x. So I'll take that 0.4, I'll distribute that. Actually, I didn't distribute it, I just put it straight into the formula here. I could have distributed it. I have the integral from 0 to 20, 0.4 times 20 minus x. Work that out on your calculator, and we have 80 joules. Now, the whole problem together would be the weight of the bucket, plus the water, plus the rope, and we'll add all of those together, and that gives us the total work done, 1,220 joules. If you're not real sure about how I came up with some of these equations, come on in tomorrow and ask, and I will be more than happy to show you. Alright, work done pumping. The conical tank below filled within 2 feet of the top. So it's 10 foot high, it's filled within 2 feet, so it goes up to 8. It's got olive oil in it, which weighs 57 pounds per cubic foot. How much work does it take to pump the oil up to the rim of the tank? First thing I would point out to you is that this tank is found by taking the line y equals 2x, you see right here, and the section between that and the y-axis, and then revolving it about the y-axis. So that is how we are coming up with this shape. And we're going to basically work this problem first by considering a little sliver right here. I just take some random sliver and I think about what it takes to get that to the top. Alright, so let's talk about the volume of this little sliver right here. That is a disk, which we find the volume of a disk by pi r squared times the thickness. Well, pi is pi. The radius would be this width right here, which you see here is 1/2 pi. And then they squared it. And then we just have some random thickness delta y. We simplify that. That becomes pi over 4y squared delta y cubic feet. Now, we know that the olive oil weighs 57 pounds per cubic foot, so I take this answer times 57 pounds, and we have 57 pi over 4 y squared delta y pounds. Now I can put this into an integral. Alright, let's think about what this integral represents. The integral represents the force here and the distance. The force is what we've just talked about here. This is the pounds right here, 57 pi over 4y squared delta y, so dy, and that's all right there. Now the distance that we're talking about is represented by this height here, 10 minus y, so that goes right here. And we are going from 0 to 8. Remember, we talked about it's filled within 2 feet of the top, so it starts down at 0 and it goes up to 8. Now we simplify this. We'll take our 57 pi over 4, which is a constant, out front, and distribute our y squared with 10y squared minus y cubed from 0 to 8. And if we plug that in, you see that it's going to take over 30,000, nearly 31,000 foot-pounds of work to pump that up to the top. Fluid pressure and fluid force. In any liquid, the fluid pressure, P, which is force per unit area, at a depth h, is given by P equals WH, where W is the weight density of the water. So the fluid pressure, you take the weight density of the water, like the olive oil in the last problem was 57 pounds per cubic foot, times the depth h, the height. Now, of course, you know what fluid pressure. You know what that is. If you go deep in a pool, you feel your ears start to pop and clog. That's the fluid pressure as acting on your ears. And the further down you go, the more pressure it pushes on you because the h value is getting larger. We're going to use this to work the next problem. Now, I'll let you read this, so pause the video if you want. But it's an interesting occurrence. Essentially, this town in this area in Boston had a molasses factory with a huge tank of molasses, which was, while it may have been okay built, was not adequately built. The pressure built up to the point where the tank could no longer contain it anymore, It exploded, and well, you see in the picture of the carnage of what happens when you have a molasses explosion. It took weeks and weeks to clean it up. Made it to other towns. It was a mess. Now I was not there personally, obviously, because it was in 1919. But you can read about it more on the internet if you choose to. So let's work a problem with the Great Molasses Flood here. Given that the tank was full of molasses weighing 100 pounds per cubic foot, what was the total force exerted by the molasses on the bottom of the tank? Now we're just talking about the bottom base at the time when it ruptured, and then part B, what was the total force against the bottom foot-wide band? So if you think about just this little part right here, because those would have been the parts that exploded. I mean, if you think about where the pressure was greatest, it would have certainly been at the bottom of the tank, and that would have been what exploded. Alright, let's start with P equals WH. Let's find the fluid pressure. Well, the weight density is 100 pounds per cubic foot, and if we're talking about the very bottom of the tank, it says it was 90 feet deep. So essentially you're looking at 9,000 pounds per square foot. So just imagine a 1 foot by 1 foot section on the bottom of the tank. There was 9,000 pounds of force being exerted on that one little area. Alright. Now, the area of the base, you think about a circular base. If it's 90 feet wide, that would be a radius of 45. We'll do pi r squared. Pi times 45 feet squared, which gives you 2,025 pi square feet. So you have that many square feet, you have that many pounds per square foot, multiply those two together, and look at that number. 57,225,526 pounds of molasses force being put on the bottom of that tank. Is it any wonder that it just exploded? Alright, part B. What was the total force against the bottom foot-wide band of the tank wall? Now we're going to do this same idea that we did up here, where we took the pressure times the area, right here. But instead of just doing it at the very base, we're going to do it from the base up for a foot, so from 89 to 90. Alright? So the pressure, which was, again, 100 pounds per square foot, times the area. And the area we're talking about here is this area that's along the bottom. Well, to get that area, imagine doing the circumference of a circle, which is 2 pi r, which is 2 pi r. So 2 pi times 45, and then multiplying it just by some height to get the width there, so that would be the y value there. And now we work that out. 100 times 2 pi times 45 is 9,000 pi, and we have y dy, and that comes out to be 2,530,553 pounds of pressure. So, I mean, you look at this much at the bottom, that much just at the bottom foot combined. No surprise at all that that absolutely exploded. Now, last thing we're going to look at is the idea of statistics, normal probabilities. Hopefully by now all of you know what a normal probability is. If you have a large enough population, things that are distributed normally, you have more things in the middle average group, and then as you go out there's a symmetry as you move out, and you get a nice looking bell curve. You know, if we think about A's and B's and C's and D's and all in the class, you should have more C's than anything else. You should have an equal number of B's and D's, and you should have an equal number of A's and F's. This is a normal probability. Now, the probability can be looked at using integrals instead of just what you may have looked at in statistics. First of all, we have the normal probability density function, or what we call a Gaussian curve, for a population with a mean of mu, if you know what mu is, the Greek letter mu, and a standard deviation sigma. This is a lowercase sigma, not what we're used to seeing with the capital K sigma. But it is this function right here. F of x equals 1 over sigma, radical 2 pi, e to the negative x minus mu squared over 2 sigma squared. This is a normal distribution function, essentially, right here. Now, you probably did not discuss that in probability and statistics, but that is what it is. We're at the end of this video. We'll come back and finish it in the next one.